Hello everyone, and here we are at 612, where by the end of this video, we're going to know how to take the derivative of exponential functions. So we're adding to our repertoire of what we can take the derivative of, or in other words, what we can differentiate. So the goal of this video is that by the end of it, we will know how to derivative exponential functions, which is any function that's in that form. All right? So let's recall where I left off on the last video. So in the last video, we explored three functions. We explored e to the x, 2 to the x, and 3 to the x. Okay. Now, if you remember, what happened is we looked at a graph of each of these, comparing the function to its derivative. And I'm going to do a quick sketch here to recap what we found out. So if I graph 2 to the x, it looked something like this. But then if I was to graph, and I'll do it in red, if I was to graph the derivative of 2 to the x, well, the idea, before I keep going, is on 2 to the x at 0, we'd be at 1. But on the derivative of this function, which we don't know what it is, right? That's what we're exploring, is what happened was it actually grew at a slower rate, where at 0, it was at point, what was it now? I have it over here. It was at point, where did I put it now? Apologize. I have it over here? No, I don't. Ooh, maybe it's on this one. 0.693. There you go. It was at 0.693. Sorry about that. And then what was fascinating about that is if we graphed e to the x, which again, remember e is Euler's number, it's approximately 2.71828, right? Is e to the x looks something like this at 1. And then the derivative of e to the x, which was fascinating, was actually the function itself. It was the same function. But then if we did 3 to the x, here's 3 to the x, crossing at 1. At that same value, the derivative of 3x is actually a little bit higher at 1.099, meaning it's increasing faster. So what that found out, and where we're getting left off at as we continue this, is that what we knew from the last video is that the derivative of 2 to the x was something like 0.693 times 2 to the x. It was some constant times that function 2 to the x. And e to the x was actually e to the x, which what that means in front is actually the constant 1. Right? The derivative of e to the x is the function itself. And then when we did the derivative of 3 to the x, that constant in front was 1.099 times 3 to the x. So the idea is with these exponential functions, we know that there's some constant front, but where are these coming from and how can we generalize that? Okay, so what's important is that we take away this. This one's a big one. The derivative of e to the x is e to the x. So what that means, again, I'm giving some background on this, is that for any generic function, a to the x, this will equal a to the x if a is equal to e. All right? So why that is the fact that we can stay where we're at. E is such a special value. Is e, what they call, might say, is very natural, is the natural number or unit for exponential functions. I almost wrote exponential, I apologize. For exponential functions. Okay? Because of this fact right here. Now, we could write that as y equals e to the x is natural. And how that relates is that the inverse of this function, remember that for talking about exponentials, the inverse is typically a log. It's typically a log function, because that's what allows us to bring the exponent in front. But because e is so natural, there's actually what's called a natural log. And that is denoted by ln on your calculator. All right, and that is big. So ln. And this right here, this natural log function, is the inverse for y equals e to the x. Now, a little background about that is ln, you might be saying, why is it ln if it's natural log nl? Why isn't this flipped backwards? Remember, when a lot of this language was discovered, it was in ancient Europe, and ln was in Latin, and it actually, in Latin, stands for logarithmus naturalis, the natural log, which allows us to have the inverse of the natural number for exponentials. So basically what I'm saying is y equals e to the x is an inverse with y equals natural log of x. All right? They're inverses of each other. Now, you might be thinking, why does that even matter? What's inverse mean again? Now, the value of an inverse, that means like with this implies, that if you were to have the natural log of e to the x, because you have an inverse of an inverse, because these are inverses, that's just going to result in x. And because they're inverses, you could say that e to the natural log of x, because these are inverses of each other, will also just result in x. And that's big. All right. Now I'm going to do a side note of why that is. All right. Inverses of each other. Now, why is that? So, proof of each of these. So I'll do the one on the left first. So natural log of e to the x. And say we didn't know what it equals. So let's say equals what? Now, I guess one thing I could have said previously was when I say natural log, and we could have logged both sides, I'll have it up here, make sure it's showing. So I could have done log, but remember that if I do log, it's generally base 10. If there's nothing there, it's base 10. Well, for the natural log, it would be y equals log base e to the x. But because it's so popular in so many realms of math, they didn't want to keep writing log e, so this is the same as y equals ln of x. All right. So just keep in mind log base e is the same as natural log. Okay. So proof, why does this equal x really quick? So if we were to do this, this is base e. So if we were to write this in exponential form, we'd be saying e to what power equals e to the x. That's how you convert logs to exponential form. Well then, if that's the case, then that implies that that has to equal x, which therefore it is. What about this one over here? Why does this equal x if you wanted to see it? If you wanted to say, what does that equal? Well, we would natural log both sides. And we do that, remember, to bring that exponent out in front by log properties. So natural log of x times natural log of e equals natural log of what? Well, since natural log is base e, these are going to go to 1 because it's like e to what power equals e? Well, that's just 1. So you get NL of x times 1 equals ln of what? And then if that's the case, then that implies that x has to equal whatever that is. Therefore, e to the natural log of x is equal to x. And this is going to help us with the derivative. So we're building up into it, right? So e is your natural exponential number. The inverse of that is what's called natural log, because logs are inverses of exponentials, but with e being such a natural number that makes it all work with derivatives, there's a special log for it. All right, so where does this take us? I keep going at this rate. So let's do an example really quick. using this identity, help you understand. So if I said solve e to the 10x plus 1 equals 7, how would you solve this? So you would log both sides, which again, you could do log, but you'd have to specify e. You don't want to use log base 10, as that wouldn't help us here. So if you wanted to do that, you could. It's just not common in the math community. So it's better if you do natural log of both sides when we're working with e. All right. So we take the natural log. That allows us to bring the exponent out in front. Natural log of e is going to be 1. So this is all going to go to 1. E to the first equals e. You get 10x plus 1 equals natural log of 7. Now remember that this is just a number. Natural log of 7 is, this is just saying e to what power equals 7. That's what this is saying right here. Okay. So solving for x, then we would have x is going to be natural log of 7 minus 1 over 10. And there's the idea of using the inverse in solving problems. Okay. Now, this leads us to the idea, how does this help with the derivative of a to the x for any generic a? Because all I've basically said so far is the inverse of e to the x. How does this help with ax for any a? Okay. So let's look at this through an example. So let's do, what's the derivative of 2? Well, that's your class for problem. I don't want to do 2. Change it up just slightly. What's the derivative of 3 to the x? Okay. Well, we can rewrite 3 to the x as e to the natural log of 3. And then we can actually raise all of that to the power. So it's the derivative of e to the natural log of 3 raised to the power of x. This is the same thing. Now, remember why that is. So if you forget why, so e to the natural log of 3 is just going to equal 3. And then also remember that if you have like a power raised to a power, so if you do x to the 5th raised to the 2nd power, well, that's equivalent to saying x and then making that multiplication of 5 times 2. So the idea of raising it to the power of x, that's just the same thing as multiplying these two, and we could write it that way. So 3 to the x is the same as e to the natural log of 3 to the x. That's the same thing. All right. Well, if we take we know that the derivative of e to the x, remember that we know that d dx of e to the x is just e to the x. Now we're going to use that with the chain rule to be able to do this. So if we get back to this problem, the derivative of e to the natural log of 3x means that's the derivative of e to the x, so it's e to the natural log of 3 of x times, so the derivative of e, leaving the inside alone, so this is using the chain rule, times the derivative of the inside, where this is considered like the inside. Well, what's the derivative of natural log 3? So times d dx of ln 3 of x, if I write this all. Well, by chain rule, then we have e to the natural log of 3x times natural log of 3. And then if I was to re-put e to the ln of 3x back to 3 to the x, then I can actually write this as 3 to the x times natural log of 3. But it's typically more common to put the natural log in front because this is just some constant, right? Times 3 to the x. And there's your derivative. So in hindsight, the derivative of 3 to the x is equal to natural log of 3 times 3 to the x. Good. Now, how does that apply with e to the x? Let's look at a few more examples. So what if I did, wait a second, am I picking onto something? What if I did e to the x? Well, we know already that it's going to be e to the x. But how does that work with this? Well, we would do the derivative of e to the x would be natural log of your base, which my base here is e, times that same function, times e to the x. But what's natural log of e? Remember that natural log of e to what gives you e is just 1. So that's 1 times e to the x, which is just e to the x. And there you have it. So what is that in general? Let's generalize this. So generalizing the derivative of an exponential, a to the x for any given a, is going to equal the natural log of that base, that's your coefficient, times that function e to the x, where only e makes that natural log become 1. And that is one of the final, we have like one more, and that's derivatives of logs, but you are more or less adding to your toolkit to be able to differentiate every single type of function out there. Okay. So let me do a few more examples with you, and then I'll be done with this video. Example 1, what if I said, what's the derivative of 5 to the x? Okay, so now that you know that derivative rule, we would just say it's the natural log of the base times that same function. So that's the coefficient that provides the stretch on the graph, if you remember from the beginning. So that's your answer. And I want to show you this really quick. So back at yesterday's video, when I talked about, we found this out. Well, what is 0.693? That is natural log of 2. 1 is natural log of e. 1.099 is natural log of 3. So that's what the exact value is that we're going to be using now. So there's my first example, example 2. What if I gave a more complicated problem of 5 to the 6x minus 4 to the x to the third? All right. So don't forget chain rule. It's huge. So derivative of the outside, and we're taking the derivative of this function with respect to x. So derivative outside is going to be natural log of the base times 5, leaving the inside alone, where this is like the inside, times the derivative of the inside, and the derivative of 6x is 6. And then we have minus, what's the derivative of this function? Well, again, it's the derivative of the outside. So the derivative of exponential is natural log of the base times the function itself, times the derivative of the inside. The derivative of x to the third is 3x squared. And there's your answer in just a really messy format. So if I clean it up, typically put the x's at the end. So it would be 6 natural log of 5 times 5 to the 6x minus natural log of 4 times 4x to the third times 3x squared. And there you go. That's the derivative of that function, that box. All right, 2 more. Example 3 is, what if I did e to the 5x and take the derivative of that? All right. Now, in case you forget, because you don't necessarily have to memorize the special cases, you would do natural log of the base, so it'd be natural log of e times e to the 5x. And then with chain rule, we have to differentiate the inside, so derivative of the outside, leaving the inside alone, times the derivative of the inside, which is 5. Where natural log of e is just going to go to 1, so we're just going to be left with 5e to the 5x. That's our answer there. I don't know if you can see that clearly. So that's the derivative of that. And the very last example, just to show you working with trig functions, what's e to the cotangent of x plus 2 to the cosecant of x, and we differentiate that. Well, that's going to be e to the cotangent of x times the derivative of cotangent of x, and the derivative of cotangent is negative cosecant squared of x, plus the derivative of 2 cosecant x is natural log of 2 times 2 to the cosecant x times the derivative of the inside. The derivative of cosecant x is negative cosecant x cotangent x. And there's your derivative function in an unclean manner, but it is the function. Okay. So there it is. I hope this makes more sense to you and you're able to now differentiate an additional type of function in your arsenal. If you have any questions, please reach out. Bye-bye.